So let's talk about substitution matrix in a bit more detail. So remember we said that substitution matrix is integral to the scoring scheme. But what does it really do? Well, the substitution matrix is what controls the cost of the mutations in your alignments. So substitutions that are more likely usually get a higher score, and substitutions that are less likely obviously get a lower score. An appropriate substitution matrix can help with the determination of the likelihood of homology between your two sequences. So when you are doing an alignment, think about the type of substitution matrix that's appropriate for the comparisons that you have in mind. So what options do we have in this regard? Well, the sequences that we compare fall into categories. You have the nucleic acids, which is DNA most of the time, and we can have amino acids or proteins. So for DNA or genes, we can use a percent identity matrix, which will go for just the matches that happen to align very well in your pair of sequences that you're looking at. Or you could go for something a little bit more elaborate, like we can see that, like we shall see later. For the proteins, obviously there are two main matrices that we rely on. One of them is the percent accepted mutations, and the thinking behind that, or the strategy around it, is that it's able to estimate the rate at which each possible residue in your sequence can change into another one over time. And it has that evolutionary history behind it. And so there are comparisons where that's really very important, and you think that evolutionary relationship should not be ignored. And so for that, you may go for this percentage accepted mutation. Or you could go for the blossom. This one is derived from alignments as indicated from the blocks database. And the thinking here is that a blossom X will be able to identify best sequences that have diverged up to X% of divergence from your query sequences. So if you think you have this kind of information, then, and you think this is the matrix that's best for your alignments, then you choose that one. We shall talk more about the individual matrices later on. Well, for DNA scoring matrices, they can be approached in two ways. You can have one where you're only looking at the proportions of identical residues that have been aligned in your alignment. In other words, the exact matches. And those are the ones you get to score, just like in the alignment of sequence 1 and sequence 2 as shown above. However, there are times when that's not sufficient and you want a more elaborate system. There you can have one where you're looking at substitutions and even gaps where they happen. And for this, you can design a more elaborate penalty scheme for that. For example, one of the popular programs that's used for DNA sequence alignment, BioEdit, has a default scoring system, and if you went to its pages and looked this up, you should be able to find out what scoring system they're using. And for that, they have a match that goes for +2, not +1 like here, and a mismatch there is scored as -1, and it has a gap opening penalty and a gap extension penalty that has a certain figure associated with it. However, note that usually if one is really looking for the evolutionary relationship between two proteins, aligning the protein sequence is much better than aligning the DNA. So what most people really do is they convert their DNA sequences, if this happens to be a gene, into the protein sequence, and then it's really the proteins that's aligned. And the reason for this is that DNA has only 4 bases, as you can see here. And so it's easier to find a chance alignment when you are working from a space of only 4 possibilities than it is with proteins which have a subset of 20 amino acids to pick from. So the alignment from proteins is much more robust. Also, DNA evolves more rapidly than proteins. And then remember that one base mutation in DNA always doesn't mean you're going to have a different amino acids being coded. Remember, at the 3rd position, you have that wobble base pairing which allows for flexibility in the genetic code. So because of that, the change in just one position at the DNA level does not necessarily mean that the protein, has changed there. So all those things factored in makes it way better to use protein or amino acid alignments where possible. And also one other thing is that some protein alignment matrices have evolutionary information embedded into them, so that makes them even more suitable for aligning. So how about the protein scoring systems themselves? So generally, these matrices really factor, or they reflect, the mutation or evolutionary barrier that's associated with the conversion of one amino acid residue into another. And they factor chemical similarities of the side groups, and they factor the observed mutation frequencies, and also the probability of the occurrence of each amino acid residue, or the frequencies. So that's really factored. And there are two main ones to choose from. You have the palm family and you have the blossom family, as we shall see later on. So percent accepted mutation, or the palm. So there are several variants of the palm. So it's really a family of matrices here, and it's the only matrix that's based on evolutionary considerations. So this matrix tracks evolutionary origin of proteins, or it tries to, and each family tries to give the changes expected for a given period of evolutionary time. That's how it's derived, really. So the predicted changes that are used to produce the alignments between two proteins and to score it have an underlying assumptions. And the assumption is that the substitutions that are observed over a shorter period of evolutionary history can be extrapolated to longer periods of higher palms. So you can start your calculation based on, say, a 1% divergence of sequences from your reference or something. And then those values that you get, the underlying assumption in this mutation, in this matrix, is that you can then extrapolate those to even longer evolutionary distances. And when you are dealing with sequences that are even more diverged than the ones that were used to calculate the earlier palm, that higher palm should be able to work with those more diverged mutations or sequences equally well. So the palms were first instituted or initiated in 1978 by Dehoff when he calculated the palm1 matrix, which, like I've earlier said, reflects an average change of 1% of all amino acid positions in the alignments that are under considerations. Now, the common palm 250 that's mostly used in many alignments, and all the other palm family members other than the palm1 are just extrapolations. So the underlying palm1 data can be used to extrapolate for additional distance matrices under the palm family. For example, the palm 250 will be an extrapolation whereby you're thinking that you can have a 250% change that's expected in about 2,500 million years of divergence. Remember, the thinking here is not to think of the 250% chance, is that for the positions that are under considerations, you can have one position mutate from itself and then back to itself and then through other positions. So intuitively, it's hard to think of a 250% change from 100. From the highest one would think of is 100%. But if you also allow that some amino acid may look the same, but they could have changed all the same and back, then you can visually now see where the 250% can come from. Now, the other thing to think is that because you have families of palms, some have higher numbers, others have lower numbers, how do you really work with those? So the rule of thumb, or the guideline, is that the higher palms are better with alignments than the lower palms if you're looking at distantly related proteins. But if you're looking at more closely related proteins, the lower numbered palms will give you better alignment. As an example, the palm 120 can be used for alignment, for aligning sequences with, say, 40% similarity, whereby the palm 60, will be good for aligning sequences with 60% similarity. These are obviously more closely related, so the lower palms is used to align more closely related sequences, and the higher palm is used to align more distantly related sequences. This is an illustration of the common palm 250 matrix. Remember, like I said earlier, Dehoff in 1978 only calculated the palm 1. So the palm 250 shown here and all the other members of the palm family are really extrapolation from the palm 1 matrix. And like you can see, the amino acids are grouped according to the chemistry of their side groups, and also that the scores that you have here in the columns themselves, these are log odd scores, though in the example I'd say they're first got from the odd scores, which are then converted into logs to enable the manipulations to be much higher. So here you have, in these boxes of the palm 250 matrices, you have the log odd scores multiplied by 10 to give these numbers that you can see here, and then those are the ones that are used to do obviously the scoring. So what the numbers themselves really mean is that where you have a high score, for example like this, a plus 10, that means that the ancestral probability is greater there. So you can be confident that in that position, aligning those two residues, so aligning a Y with a Y, means that those two positions from both sequences, the ancestral relationship is very much probable. Whereas when you have a lower score, for example -4, where you see a -4, it just means that that change is really random, more to do with chance than an evolutionary relationship. And so to come up with the cumulative probability for an alignment, for example, if it was of two sequences aligning Y and Y together in the two sequences, the score there will be 20. So you score the first 10 for the first YY, and then the other 10 for the next YY. So the other main substitution matrix that's used for aligning the protein residues, that's called the Blossom family of matrices. And these ones use almost a similar approach or alignment strategy to the palms, but there are some differences, especially in the way the frequencies of the target residues are estimated. For the Blossom, the underlying data is derived from the blocks database, and this one involves somehow more distantly related sequence assemblies than you had with the palm 1, which was only the 1% amino acid changes expected, and then the rest were just derivation. Here you have actual observed data from a group of sequences or database entries that span larger, evolutionary distance than in the palms. So here in the Blossoms, if you want actual observed data that's generated from alignments that have been diverged for a little bit much longer to calculate the probabilities of your alignment pairings, then you may want to consider using the Blossoms. Here is an example of the Blossom matrix, and the key thing here is that the underlying data used to calculate these positions comes from a wider sequence database than, for example, the palm. So the palm and the Blossom have distinct differences. As an example, the palm uses an evolutionary model, the Blossom does not. One usually closely related sequences, the other one has a more divergent data set, and one you have extrapolations for other distances, whereas the other one, everything is observed data. So in short, the main difference between the two is that Blossom looks at mutations directly in motifs of more diverse sequences as found in the database, whereas palm extrapolates the evolutionary information based on a small subset of related sequences. That's really your main differences. That's your main difference between the two.